So in our last lecture, we left with a little bit of a cliffhanger as far as how to express the change in entropy of the universe with respect to the system. We got as far as using delta H of the system, the delta S of the system, to express the delta S of the universe. And of course, the reason we want to do that is to determine if a reaction is going to be spontaneous or not. That's really why we want to look at the change in the entropy of the universe. Well, this lecture introduces a different term that we can use to find that spontaneity or non-spontaneity, and it uses that equation that we just learned. So if we took that last equation that we had, delta S of the universe is equal to negative delta H system over T minus delta S of the system, and we multiply both sides by a negative T, we arrive at this equation here. Minus T delta S universe is equal to delta H of the system minus T delta S of the system. Now Gibbs defined this quantity negative T delta S of the universe as the free energy change of the system, and it is named delta G. So what we have is that the delta G of the system, so the free energy of the system, which is the negative T delta S of the universe, is equal to positive delta H system minus T delta S of the system. This is a very handy equation to use to determine spontaneity, because we can relate the sign of delta G directly to the spontaneity of a reaction. So if a delta G is greater than 0, then that reaction is non-spontaneous in the forward direction. It will be spontaneous in the reverse direction. If the delta G is negative or less than 0, then it will be spontaneous in the forward direction and non-spontaneous in the reverse direction. And then if something has a delta G that's equal to 0, it means it has no preferred spontaneity in either the forward or reverse direction, and that means that the reaction is at equilibrium. So now we've been able to tie all of these thermodynamic quantities actually back to equilibrium, which is pretty exciting. So let's look at this equation, delta G equals delta H minus T delta S. We've learned how to calculate delta H and delta S for the systems using those tabulated values for the various chemicals that you have in your chemical reaction. So we have delta H was equal to the delta H's of the products minus the delta H's of the reactants, and for entropy, it was the entropy change was the entropy of the products minus entropy of the reactants. And then we just have to factor in the temperature there. Again, that temperature is a Kelvin temperature, so you always have to keep that in mind. So what is that Gibbs free energy, that delta G? Well, it represents the total energy change for the system. It is essentially the energy lost in disordering the system. Were you able to disorder the system? Now, if we look at our values of delta H and delta S, it turns out that there are sets of conditions, sets of values for delta H and delta S that will always lead to a spontaneous reaction, or always lead to a non-spontaneous reaction, or be spontaneous at high temperatures and not at low temperatures, or vice versa. And we can tabulate that and go through it. As an example, if a reaction were exothermic, in that case we know that delta H would be negative. And if delta S is positive, we always know that T is positive because it's a Kelvin temperature. So if you had a negative value, delta H, and you're subtracting a positive value, because a positive temperature times a positive delta S would give you a positive value. So you had a negative delta H minus a positive T delta S. Delta G will always be negative at any temperature. It's impossible to make that reaction go non-spontaneous. It will always be a negative value for delta G. Okay, so that's just an example of what you can do by looking at the signs of delta H and delta S. So let's look at a table of that. If delta H is exothermic and the delta S is positive, so the entropy is increasing, we're always going to have a spontaneous reaction. Delta G will always be negative. That's the example I just gave you a moment ago. If we have a delta H that's endothermic and a delta S that's positive, we kind of have two competing factors for spontaneity. An endothermic reaction is working against spontaneity, but an increase in entropy is working for spontaneity. And so the deciding factor here becomes the temperature. If you have a low temperature, then at a low temperature, your T delta S will be a small term, and it will not be enough to take a positive value, subtracting a small positive value. You're still going to end up with a positive value delta G. And so at low temperatures, your delta G will be positive and the reaction will be non-spontaneous. However, at high temperatures, the T delta S term begins to dominate. This becomes a larger positive value than the delta H. And then what you have is you have a small positive minus a large positive, and that will give you a negative value for delta G. So at high temperatures, these two conditions will give you a spontaneous reaction because delta G will be negative. Now, if we go the other way, if we have an exothermic reaction, that's working for spontaneity. And if we have a decrease in entropy, that's working against spontaneity. Now we have a similar situation to we had above it, but it's exactly opposite. So at high temperatures, what happens is this becomes a large negative value. So you have a negative value subtracting a large negative value, and that's like adding a large positive. And so you have a smaller negative adding a positive. That's going to bring that whole side on the right to a positive delta G, and that will be non-spontaneous. However, if you have a low temperature with a negative delta S, then you have a large negative value subtracting a smaller negative value, so it's like adding a small positive value. The T delta S will not be enough to raise that delta H into the positive. Delta G will remain negative, and that will give you a spontaneous reaction at low temperatures. So we can't say that something is spontaneous at high or always non-spontaneous at low or vice versa. Okay, it depends on, is it endothermic or exothermic, and does entropy increase or decrease? And then our last situation is just the opposite from our first one, where we have both factors working against spontaneity. We have an endothermic reaction, so a positive delta H minus T delta S, where the delta S is negative. So we have a decrease in entropy that's working against spontaneity. And so we're going to have a positive value here, subtracting a negative value here. That's like adding a positive. So we have a positive plus a positive. Delta G will always be positive, and that type of reaction will always be non-spontaneous. Now remember, just because something is non-spontaneous doesn't mean it can't happen. It just means that it requires energy in order for it to happen, a constant application of energy. So let's look at an example here. We can calculate things in a couple of different ways. For delta G, we've learned one. We'll learn another here in a moment. But we've learned this one. So we want to calculate the value of delta G at 25 Celsius for the formation of phosphorus trichloride from its constituent elements. This is not a formation reaction. We're just saying we're forming PCl3 from its elements. So we've got delta H's of our phosphorus, chlorine, and phosphorus trichloride. We've got our delta S's for all of those. So you have to calculate the delta H's for the reaction from here. So we need to make sure that we take all those values and get delta H of the reaction, or the delta H of the system. That's the same thing. We take all of these delta S's and we calculate delta S of the reaction, or delta S of the system. We need to take those. We use the temperature, convert that to Kelvin, and then use our delta G is equal to delta H minus T delta S. So give that one a shot. I will have the solution for that posted as a link in Canvas and in YouTube. Now, that's one way of calculating delta G. Here's another way how to do it. So we've done it from delta H, delta S, and T. We've also seen how spontaneity is a function of temperature. If we are calculating delta G at 298 Kelvin, a standard temperature, then we can use those delta H F at standard values, we can use the delta S at standard values, and that will give us a delta G of formation under standard conditions, and we can tabulate those delta G values for all of our substances. And then we can use an equation very similar to the ones that we used for enthalpy and entropy. So we have delta G is equal to the sum of the free energy of the products minus the sum of the free energy of the reactants. So once again, products minus reactants. And the little n's in front of the G's indicate that we have an extensive property here, and so we do have to use the coefficients from the balanced reaction to multiply each of those values by that balancing coefficient. So here's the same example that we did earlier. As far as the reaction, we have P2 plus 3Cl2 goes to 2PCl3, but notice now rather than using delta H and delta S, we have just delta G values, and we can use the equation that we just learned. So give that one a shot, and I will post the solution as a link in Canvas and the video on YouTube. So how can we interpret these values of delta G? We've seen how the sign of delta G predicts the spontaneity. If it's negative, it's spontaneous in the forward direction. If it's positive, it's non-spontaneous in the forward direction. It turns out that we can use that value of delta G to determine where the equilibrium lies. So if we have a large negative delta G, it indicates that that equilibrium lies way to the right-hand side. It means we are a long ways away from equilibrium under standard conditions. And so the equilibrium has to go way to the right-hand side in order to get to equilibrium. If we have a large positive delta G, it indicates that that equilibrium is far to the left. We have to shift way towards the reactant side from standard conditions in order to get to equilibrium. If you have a moderate-sized delta G of either sign, positive or negative, it indicates that that equilibrium is somewhere in the middle. Now you'll notice that we used a very similar language when we were talking about K. So there must be a link between delta G and K. And we're not going to get to that just yet, but we are going to do that next week in the upcoming lecture. So we see that there is a significant relationship between delta G and equilibrium. We know that when delta G is equal to 0, we are at equilibrium. We know that the farther away delta G is from 0, the farther away from equilibrium the reaction is. And we can also calculate the value of delta G under non-standard conditions. There's a simple adjustment to make. We're not going to go through that in this class. If you take a physical chemistry class, you'll definitely see how to do that. Well, that wraps up all of our content for week 5. And once again, if you have any questions or comments about how to do any of these calculations, make sure you check out the videos that I've posted on YouTube. And if you still have questions, make sure that you contact me. Best of luck to you.